Hi everyone, this is Professor Nowley. Today I'll be giving you a brief lecture on the metric system and how we use metric units and prefixes to quantify mass, volume, and density. Here's an overview of the presentation. I'll first talk about why we use the metric system and how we convert units in the metric system. I'll then continue with talking about the SI system of units and then how to make mass and volume measurements, as well as how to calculate density. We'll close off the presentation by discussing a couple of problems that incorporate the concepts that we discuss in this presentation. First off, let's start by saying how we express a measurement. A measurement always contains two components, a number and a unit. For example, if you want to know how much a person weighs, you will take that person and have him or her step on a scale. The scale has a unit that expresses that particular weight measurement. For example, in this case, the person stepped on the scale and the scale showed a number around 115. If the scale is based in the unit of pounds, we know that the weight of this person is about 115 pounds. The measurement therefore for weight is expressed as a number 115 followed by a unit, which is pounds. The unit that you're comfortable with, that you see very often, are what we refer to as the English units. These are units that are expressed in inches, feet, yards, ounces, pounds perhaps, fluid ounces, cups, and so on. The problem with these units is they require complex conversions among the units, and those conversions are not necessarily clear to everyone. Let me illustrate what I mean. Here are two different conversions, one for length and the other one for volume, in the English units. So as you can see at the top here, these are all length measurements in the English unit. Foot, inches, yard, miles, and so on. These are the relationship among these units. 1 foot is equal to 12 inches, 1 yard is equal to 3 feet, which are also 36 inches, and so on. What we can see is all of these numbers are related by some factor of 3. So if that's the only thing that we need to remember, then that's all fine. We know that all the units are related by a factor of 3. However, when you go to look at volume measurements, you find that a cup is 10 fluid ounces, a pint is 2 cups or 20 fluid ounces, and so on. And it turns out that volume units are related by a factor of 2 in the English units. So this makes life very complicated because in one case, for one property, length, all the units are related by factors of 3. In another property, volume, all the units are related by a factor of 2. This would drive anybody crazy if you have to learn all these different units and how they're related to each other. It'll be a lot more convenient if one unit and another is related by the same number, and regardless of the quantity, they're always related by this number. And this is what the metric system provides us. In the metric system, there's a standard unit, and then there are prefixes that are attached to the unit. The relationship between one prefix to the next prefix is always a factor of 10. So in other words, you can go from prefix 1 to prefix 2 by multiplying by a factor of 10. You can go from prefix 2 to prefix 3 by multiplying by another factor of 10, which means that you can go from prefix 1 to prefix 3 by multiplying by a factor of 10 times 10, which is 100, or 10 to the power of 2. Let's look at an example here. Length is expressed in units of meter in the metric system. 1 kilometer, so kilo is a prefix, 1 kilometer is defined as 1,000 meters, which is of course just 1 times 10 to the third meters. 1 millimeter, on the other hand, is 1/1000 of a meter, which is just 1 times 10 to the minus 3 meter. Now, the easy thing about the metric system is when you express another unit, for example, for volume in this case, the standard unit is liter. If we say 1 kiloliter, that is also equal to 1,000 liters, or 1 times 10 to the third liter. And 1 milliliter is equal to 1/1000 of a liter, or 1 times 10 to the minus 3 liter. What we can see from these two simple examples is that the prefix kilo always means multiply by 1,000 for the base unit, and the prefix milli always means take the standard unit and divide it by 1,000. As a result, with the metric system, it's fairly easy to go from very large to very small. It's just a matter of remembering these prefixes, and they're always related to the base unit by some multiple of 10. For example, here's the base unit, is always expressed as 1. Anything above it are the larger units. So 1 of the larger unit is always some multiple of 10 of the base unit. Whereas the smaller units are expressed at the bottom, and 1 of the smaller unit is always the base unit divided by some multiple of 10, either 10, 100, 1,000, or so on. One of the questions that you always have in science is comparing two different metric units. For example, which of the following is larger, 120 centimeters or 0.015 kilometers? The trick to do this type of problems is always to look at these units and convert them to their standard units, in this case meter, and then compare the sizes of the numbers. So in this case, we want to take 120 centimeters and convert it to meters. Using the previous prefix relationship table, we know that 1 meter is equal to 100 centimeters. So to convert centimeters to meter, we just have to multiply 120 by 1 over 100, and we get that that's equal to 1.2 meters. We do the same thing for kilometers. In this case, we find that 0.015 kilometers is equal to 15 meters. So it's clear by comparing these two numbers right here that 0.015 kilometer is a longer distance than 120 centimeters. In science, we often talk about something called the SI units, which stands for International System. The SI unit is a unit system that's based on the metric system, and it is the unit system that we use in scientific publications, international trade, and so on. The SI unit is very important, and it has two different groups of units. There are 7 different what's so-called base units, which are units for quantities that are not related to each other: mass, length, time, and so on. And then there is a group of the rest of the other units, which are all called derived units, and they're called derived units because the properties that these units express are always related to the base units in some relationship. An easy example is area and length. Length is our base unit. Area is a property which is expressed as length times width. Each of those properties, length and width, are expressed as units of length. So if we want to know the unit of area, it will be the unit of length squared. So if the unit of length is meter, then the unit of area must be meter squared. In other words, area has a derived unit from length, which is the base unit. Now let's talk about some basic properties that chemists regularly measure. The two properties I want to focus on are mass and volume. Mass is a measure of the amount of matter that a substance has. Normally mass is measured using a balance. As you can see here, there are two types that I'm showing. There are many more. This is an antique balance, and this is the type of balance that you'll more often see in a modern chemistry lab. It's called a digital balance, where you just put the object on top of the plate and a number will show here to indicate the mass of that object. The standard unit in SI system for mass is grams. Volume is expressing the amount of space that a substance occupies. The standard unit for volume in the SI system is cubic meters. For liquids, usually we express volume in units of liters. There's a relationship between these two units. 1 cubic decimeter is equal to 1 liter. That allows you to interconvert fairly easily between one unit and the other one. Generally for liquids, we measure the volume using volumetric glasswares of some sort. For example, a graduated cylinder. This picture here shows you all kinds of volumetric glasswares, with the graduate cylinder given here and a couple of them here. Once we measure the mass and volume of a substance, it's typical to calculate its density, which is given as the mass of a substance divided by its volume. Density is important because the value allows us to visualize what a substance might be. In particular, density values can tell us whether a substance is solid, liquid, or gas. For example, consider the following 3 different substances, all with a mass of 1 gram. If you have 1 gram of gold, it will occupy about 0.05 cubic centimeter of space. In other words, its volume is about 0.05 cubic centimeter. If you have 1 gram of water, because of the density, it will occupy about 1 cubic centimeter of space. In other words, the water will occupy about 20 times the amount of space that the gold will occupy. If you have 1 gram of air, it will occupy about 816 cubic centimeter of space. In other words, the air will occupy about 800 times the amount of space that the water occupies. You can immediately have some feel of what these different substances are. The air, which is a gas, basically has very few particles in a given amount of volume. The liquid, which is the water, has a lot more particles in the given amount of volume. And the solid, which is the gold in this case, has a lot more particles within that given amount of volume. So the air is less dense and the solid is more dense. And as density goes up, we can see that the state of matter, in this case gas, liquid, and solid, also changes. I'm going to close off this presentation by having you work on a couple of problems that are related to metric prefixes. The first one is this problem. It's asking you which of the following measurements show the longest object. You just need to make the same type of conversion calculations that I did earlier, and you should be able to get the answer. What you want to do at this point is stop the video a little bit, work on this problem, and then continue again to see what the answer is. If you did the same conversions that I did earlier to convert all of these units to the meter, for example, to a standard unit, you'll find that the answer for the longest object in this case is A. The second problem I want to ask you is also about unit conversion. However, now we're going to use squared units. In this particular case, here's a design of an apartment, and it's given at the bottom here that the size of the entire apartment is about 800 square feet. The question is, what is the size of this apartment if you want to express it in square meters, with 1 meter being given as 3.28 feet? Again, just like the previous problem, what you want to do here is stop the video, work on this problem yourself, and then continue it again to see how you're going to relate the measurement here in square meters. The answer to the problem is given here, which is 74.36 square meters. Let me just discuss briefly how I get this answer. You started with 800 square feet of area, and what you want to do is convert this value to square meters. Now, we don't have a conversion between square meters to square foot, but we do have a conversion between meter and foot, which is 1 meter to 3.28 feet. In order to make this unit into a squared unit, what you need to do is basically square that conversion factor, as I'm showing right here. So in other words, you're going to make your calculation as 800 square feet times 1 over 3.28 with the appropriate units, and then square that, and the square foot unit will cancel, and you end up with square meters as your answer. Okay, I hope this video explains to you the metric system as well as a couple other properties that you're going to need to understand before you come to the workshop. When you come into the workshop, one of the exercises that I'm going to ask you to do is to make these kind of unit conversion calculation, and you'll also be expected to design an experiment to figure out a physical property of a substance. I will see you at the workshop.